multi-armed bandits was started a bit in terms of medical trials. So the first situations where this kind of problem came up was where you had a drug. Okay, so it wasn't gambling machines, although the name is after these gambling machines. You had a drug and a number of different drugs, and you could apply the drug to a patient to see if they got better or not. Okay, and obviously if you give patient A, the first patient who comes along, a drug, okay, you can't give them the other drugs, okay, because you wouldn't know which one was working. So you just have a choice to make, and then you don't know what would have happened, okay, if you'd given them the other drugs, okay, and then you can see if the patient gets better or not, or if they die, or if they live, or whatever, whatever your metric is for deciding how well that treatment worked, okay. And so this is the kind of issue they had in kind of drug trials, where you've got a number of patients, you have to determine which is the best drug. Obviously, you don't want to explore too much because you might end up killing lots of people. You want to basically find out as quickly as possible which is the best performing drug, okay? And so that was sort of where this multi-armed bandit problem first arose, okay? And in fact, still today, I went to a course in Lancaster where they had a guy who was talking about how they're using these kind of ideas in medical trials and how you can use sort of Bayesian statistics along with multi-armed bandits to try and determine how long you should run a drug trial for. Okay, so if you try a drug 5 times and everyone's not got better, then maybe you should consider not continuing with that drug and giving people a drug that actually does work, given the data so far. And it comes down to making those decisions as to when you should stop exploring an arm and when you should, or stop exploring an option and start a new one, okay? All right. Okay, so enough about that. So let's go through one type of multi-armed bandit problem. Okay, and like I said, this is a non-stochastic version because I'm not assuming there's any statistical distribution associated with the reward process. Okay, and like I say, that's quite different when this comes into investment problems. This is probably quite different to the way that you've been looking at problems in an investment and studying stock prices and all the rest of it, because you've been assuming, okay, that all of the stochastic processes you've been dealing with have been some sort of diffusion process. Okay. And here we're just saying, like, it's just noise, it's just stuff, and we don't really know if it's going to go up or down, okay? All you have to do is summarize the advice that you've been given about that and then try to follow the best advice that you've seen so far. Okay, so that's a very different way of looking at investment problems to the way that we've covered things, okay? Okay. All right, so just to recap from last time, multi-armed bandit problem is a problem where you've got a number of slot machines. You pull an arm on a slot machine, you only see the reward that you get from the machine that you played, okay? And you have to explore between the different slot machines to figure out which ones are good and which ones are going to lose you lots of money, okay? And so there's the exploration part, but also you want to exploit to be able to determine which is the best machine and try to stick with that one. Obviously, if you exploit too quickly, you don't learn enough information about the machines, and if you explore too much, you're losing money because you're spending time investigating machines which are actually losing you money. Okay? Right. Okay, so that's the setup. So a bandit policy, like I say, is a policy where the choice that you make at time t is a function of the previous actions that you've chosen in your policy and the costs associated with them. Okay? i.e., you cannot observe what cost you would have incurred if you'd taken a different action, okay? And as we discussed last time, we consider a version of the weighted majority algorithm for this multi-armed bandit problem, okay? And here, there was a slight change, so the idea was the same. We had some weights associated with action, or arm, okay? And we updated by taking e to the, in this case, instantaneous cost of playing that arm, okay? So we continue to do that, but the way that we evaluate the cost is not just the actual cost we observed, but the cost and then renormalized by the probability that we actually tried that arm, okay? So if we found that we tried an arm and it earned us lots of money, but the probability of trying it, okay, was really low, then we think, well, I better compensate for that, because if I've tried an arm and it's actually been a good reward and my prediction for that arm is really low, then I should probably make more assertive action to renormalize or account for that. Okay? Whereas if the cost is really low, okay, so it's really low cost and the prediction is really high, okay, then I probably want to think that I'm kind of on for a winner here. I don't want to change things too much. Okay, so I mean, that's going to give you how we kind of assess the different types of costs here. Okay, all right. So the proof technique is going to follow similar to before, very much in the same vein as the weighted majority algorithm. Okay, I just want to show you that the essential components of that proof can be applied in this setting as well. Okay, so I want you to get an idea of the proof structure in a different setting. Okay, so the proof structure is the same. We had these weights, the capital W of t, all right? We focused on coming up with an upper bound for those weights, all right? So last time it was using Azuma's, sorry, I will say Azuma, Hofting's inequality. Hofting's the probability one, Azuma's the Martingale one, sorry. Hofting's inequality, okay? And then we use a kind of trivial lower bound, which said that the sum of the weights is less than the biggest weight, okay? And then we just put it together, and then we ended up with a regret bound. That's exactly what we're going to do again. All right? Okay, so what's the bound we're going to end up with? So where eta is the parameter here that I use for determining the values of the different costs, okay, then we're going to show that the regret is less than 1 over eta log n, eta divided by 2 t times n, and this new capital N wasn't there previously, okay? And that was the kind of cost we had to incur for the fact that we don't gather information about all the arms simultaneously like we did in the previous example. We only get information from the one that we try, okay? And for an appropriate choice of eta, okay, then we can get a bound that looks like this, okay? All right. Okay, so any questions about that? So now we're going to try and prove this result. Okay, so the first part is going to be our upper bound that we're going to use instead of Azuma's inequality. I mean, Hofting's inequality. Okay. Okay, so the upper bound that we're going to have is e to the minus c is less than or equal to 1 minus, and that should be a c, apologies, little c plus c squared divided by 2. Okay? So why might that be true? Any thoughts? How would I show that? So essentially these, notice, are the first 3 terms in the Taylor expansion of the exponential. Okay? So we know from Taylor that e to the minus c is equal to 1 minus c plus c squared over 2, okay? And then we can include the third term in the Taylor expansion, okay? But we always do it for a for a term in between c and 0. Notice we're doing this Taylor expansion about 0 going up to minus c. Okay, so we end up with this being, well, let me get it right. I think we go like c tilde cubed divided by 3 factorial for c tilde belonging to 0 to c. Okay? So remember, we've got Taylor's approximation, and there's always like a residual term left over from Taylor, okay? And the residual term is given by the next term in the Taylor expansion, okay? And then, well, since that's belonging to 0 to c, that guy's a negative number, okay? So that's always going to be less than 1 minus c plus c squared divided by 2. Okay? So that's just the okay. Remember that this form of the Taylor series is essentially the is it mean value theorem or intermediate value theorem? I think it's intermediate value theorem. So it's essentially the kind of point where you cross the 0 axis, which is the simple version of that. So it's always going to be a term in between the 0 where you started from in the Taylor expansion and c where you're wanting to end up. Okay. So that's something that's generally true about all series. You know, if you've got one of these series where the signs alternate, you can always perform bounds up to upper and below to any form of accuracy, because if you know there's a negative sign in the coefficient and the coefficient's positive, then you can always come up with lots of bounds. It's also a really handy way of coming up with different bounds for different sorts of functions. Okay? All right. Anyway, next thing, so that's going to be a bound that we're going to use. Okay? In an exam situation, I'll probably just tell you what the bound is, yeah? I'll just go like, that's it. Okay? All right. Answer for the next bit. We're going to show, so I'm just going to collect together several facts now, okay? And then we're going to launch into the main bit of the proof, okay? So we'll just, first fact is like some bound that we're going to use, which is going to be handy. Next fact is going to be the following, that the expected value of that c hat function is equal to c of a, okay? So remember, let's just get it here, that C of A is defined to be C of A times the outcome divided by the probability that I choose it times the indicator function that I try it. Okay? So let's just write down the definition. Okay. Now, notice none of this is random. Okay. Omega here I said is non-random. We're doing a non-stochastic problem. A is not random. T is not random. The only thing that's random is the choice of the policy at time t. Okay. What's the probability that at time t I choose A? Okay, so I heard someone say it in the background. So at least one person said it. So it's PT of A, yeah? All right, so this is just equal to the same thing as before, times the probability of that guy, which is PT of A, which then cancels out and gives me the answer I wanted. Okay? Okay? Right. Next one. All right, so now let's prove that if I times PTA times the expected value of the same function squared, I get something that's less than or equal to 1. Okay? Essentially, the idea is exactly the same as before. Okay? So I just look at this guy. I substitute in the value of it, which is this, and I'm going to square it. So that's this term inside here, and I can square the whole thing. If I square an indicator function, I just get an indicator function again, so that's not going to affect anything. So I'm just going to squares on these guys. Okay? And so you can notice that by the same arguments before, I'm going to get a PTA divided by PTA squared, and then for the probability of this guy is going to be PTA as well. Okay? So I just end up with PTA squared divided by PTA squared times C. Okay? This is PTA CA omega T squared divided by PTA squared times PTA. Right? Which is just C of A of omega T squared. And I've assumed, like before, that the rewards are in the interval 0 to 1. Here I'm assuming that the costs are in an interval 0 to 1. Okay, so you've got cost between 0 and 1. So the square of something between 0 and 1 is less than or equal to 1. Okay, so here we're assuming, where did I write it down? Yes, here. I'm assuming here that the costs are between 0 and 1, so we're kind of safe. All right? All right. Last one, last fact. Okay. This kind of messed with my head first time I saw it, because I was like, haven't we just done this calculation already? Because that's just the, isn't that just the expected value here? Okay? I mean, it's not, because remember, here we're evaluating a random variable, the policy, okay? Here, we've just got some random variables, and we're not taking expectation of those, we're just applying some weights to them, okay? So when I first saw this proof, I was a bit like, what's going on here? This is really weird. Here, I'm taking an expectation, and I'm replacing these indicator functions with probabilities, okay? Here, I'm not doing that. I'm keeping the indicator functions, and I'm just applying some weights to each of these functions, okay? Does that make sense? So I'm not doing an expectation. This is not meant to be, I'm not removing the indicator function of this random variable and just applying a weight to taking an average of these random variables. Okay? Does that make sense? Okay. So I just say here, note we're not taking expectation with respect to pi t, but we're taking a sum weighted by PTA. All right? And the claim is that I can somehow extract out the policy, the cost of the policy from this, which is going to be useful to us because we want to know what the regret is of our policy. Okay? Right. And again, it's really just definition. So we've got PTA C hat at time t of A of omega, which is sum of PT of A of C A of omega divided by PT of A, indicator function pi of t equals A. All right. And then, like before, these PTAs cancel out. All I'm left with is the sum, where the only non-zero term in this sum over the sets of actions or choices that I can take is the one when I make my policy choice. Okay? So the only non-zero term in this sum is C of pi of t of omega. All right? So I think it's quite nice how those little calculations you can extract out the costs by taking an expectation, you get the cost of an action. By taking a weighted sum, you get the cost of the policy. I think it's kind of cool. When I first saw that, I was a bit confused, and I was like, how does this proof even work? Because this isn't the standard way of proving this result. So there's another method that one uses more commonly. But I just think it's so simple compared to that other proof. It's worth doing it this way. Okay? It's maybe too simple, but anyway, okay. All right, now we've collected some facts together, all right? now we're going to, if I can keep my handwriting small enough, let me get my notes before I forget. We're going to we're going to kind of do the calculations similar to before, okay? So let me get the right page here so I don't make loads of mistakes and things like that, okay? Right. So we're going to do almost exactly the same thing as we did previously. Okay, so I want to prove that Wt plus 1 is less than or equal to n times some product. Okay? So, since we covered this yesterday, and it's on your practice exam, what should I do first? What do I do here? So I've got Wt plus 1. Yeah, I think the lady over here, that means do this interpolating product thing. Yeah? Okay. I'll take that as, okay. And I should be doing it from 1, shouldn't I? Okay. Okay. All right, and I can use the same trick as before. All right. That this, and I'm going to try my best to write small. Well, firstly, let's say W of 1 is equal to n, so I can make that an n. Next thing is that this is really a sum. Okay. And remember, like before, this is the sum over all the actions. Okay. Wt plus 1 is e to the minus eta. Okay. The cost of that action against the outcome that occurs at time t times little t of a. Okay. So that's another way of writing Wt plus 1 of a. I can write it like this. Okay. And I divide the whole thing by Wt. Okay, so I've just expanded this out as the sum of the weights at time t plus 1, and the weights at time t plus 1 are just multiplied by this cost, e to the minus e to this cost. Okay? Was that a little bit fast, or is that okay? That calculation. All right? So I kind of did two things at once there. Okay? And then we notice that Wt A divided by Wt is actually the probability, okay, that I try out action A. Okay? Okay? Now, at this point, previously, everything up until this point is exactly the same. In this answer, everything up to here is the same as the previous argument that we did yesterday. Okay? At this point in the argument previously yesterday, we applied the Hofting inequality. Okay? And I said to you, we're not using Hofting anymore, we're using this different inequality. Okay? So at this point, we're going to use that different inequality. The one just up here, this guy. Okay? All right, so we reached the point where we're going to apply Hofting. I said, don't apply Hofting, use this. Okay, so we're going to use this. Okay? So this, E, over here, e to the minus e to c, okay, is less than or equal to n product t equals 1 to t. All right, and I'm going to keep the sum over p the same. And we're going to put in instead 1 minus eta c of A of omega t plus eta squared divided by 2 c of A of omega t squared. All right, that's just the inequality from before. So that's, just remember the exercise, it was exercise 26, yeah? 126. Okay? All right, now we have to kind of check back over all our facts. Okay? So, what is the sum of all the probabilities times 1? Yeah, it's 1. Okay, that's the easy one. So I can take the probabilities inside the brackets here and just get a 1. What is the sum over A of the cost of A? So if I take the weighted sum of these costs, what do I get? So it's one of the things from earlier. Yeah, C pi. Yeah, thank you. We've got minus C pi at T omega T. So that from there comes from the exercise just before exercise 129. Okay? So that's exercise 129. Okay? And then we've got some stuff that I can't deal with quite yet. So we're just going to leave it. Oh, and I'm realizing my answer, I've got a typo. That should be a half there. Okay. Oh, and I should have hats on here. I'm just realizing some more typos. Hat. That should be a hat. That should be a hat. That should be a hat. And we're good. That should be a hat. Good. Okay. All right. Okay. Which is what we wanted up here. Okay. So very similar idea to the previous proof, slightly different upper bound, and then we had some facts that we collated together which we're using here to get the final result. Okay? Okay. So now, how might I show this inequality here? So the upper bound bit involved this kind of interpolating product, okay? The lower bound bit just involves saying that WT is the sum, okay, of all the weights, okay? So we're just going to use that fact. Okay. And notice each of these weights is really just the sum of all these kind of renormalized costs. Okay? So actually, e to the minus eta sum of t equals 1 to t c hat a of omega t. So why is that? Well, because I'll let you copy that down and I'll show you. All right, so why is this true? Well, because I said that the weights here, each weight we multiply by e to the minus eta, this renormalized cost, okay? And if I iterate back, I'll just get 1 for every cost that I've incurred so far, okay? So essentially this is e to the sum of these costs, okay? That's why that is. Okay. And then all I do is I take logs. Well, one thing I'll do, sorry. I'll notice that this is a sum over a, sorry. And if I want it for one specific value of a, well, then it's always less than this for one specific value of a. Okay? Let's say a dash, just so we're not confusing it with these a's. Okay? For any a dash that I like, I can always say this inequality is true. Okay? And then just take logs. Okay. All right, we're now nearly there. So we've got an upper bound for this wt plus 1 function. We've got a lower bound for this wt plus 1 function. So we just kind of put them together. All right. So that's what this is asking you to do now. Just put the two bounds together and then maybe kind of rearrange a little bit. Okay, so let's do that. Okay, so, all right. So our upper bound, okay, our lower bound here gives us that sum of t equals 1 to t c hat of t of a of omega, oh, I need an eta on here, apologies, okay, is less than log of w t plus 1, okay? And I've got an upper bound on wt plus 1, so I get an upper bound over here, taking logs. So let's just remember from the top, wt plus 1 is less than this product, okay? So log of wt plus 1 is less than the log of this product, okay? So this is going to be less than log of n, which is the first term in that product. I'll just get it here so I don't copy things down wrong. Plus the sum of t equals 1 to t, okay, log of the thing that was inside the product, 1 minus eta the cost, the following policy pi at time t, times omega t, plus eta squared divided by 2, sum over the actions p, t, a, c hat, and I'm running out of space, c, a, t, omega t squared. Okay? Oh, and it's all inside the logarithm, so I've got a brackets there for this brackets. Okay? Now, we've kind of picked this term up correctly. We've picked this term up basically correctly. We haven't got the cost of the policy, which would be the sum of these costs. Okay? We didn't pick up this term over here either. Okay? And the reason is because we've got a logarithm there and we want to get rid of the logarithm. Okay? So we use my favorite bound for getting rid of logarithms. that log of 1 plus x is less than or equal to x. Okay? Basically assuming this is relatively small in compared to 1, which is going to be, this is going to be quite a tight inequality. All right? So I'm just going to use that. Okay? So this is less than or equal to log of n plus sum t equals 1 to t minus eta c of pi of t omega t plus eta squared divided by 2 sum of a pt of a c hat t a omega t squared. Okay. Again, if I asked you this in an exam setting, I'd probably tell you the inequality that we're going to be using. Okay. I'm just going to dump you to go like okay. After you've been doing these things for a while, you get an idea of what inequalities are going to work well for you, which ones aren't. But okay. Now you can notice this is just the sum of the costs of the policy. Okay. So this is really just minus eta ct of the policy that we're considering, which this is exponential explore exploit. Okay. And I just rearrange and divide by eta. Okay. All right. So if I just move that onto this side, I've got everything that's here, but just multiply by eta. So I divide by eta, which is a positive number, and then I've got the bound. Okay. Is everyone all right with that? So we're basically done. I could write that all out, but I just write that out again, basically. So we go directly from here to there. Okay. All right, and we're very close to done. The only thing we need to now do is take expectations on this guy, and we're going to recover all the terms that we want. So that's the kind of magic thing about all those little lemmas that we had before. So I want to show that the regret is this. So we're now basically at the point where we can show the result. Okay. So basically just take expectations on 132. Okay, so we've got, and I'll copy it down. So we'll have, let's take expectations on both sides. Okay, so we're going to get E of C of the policy cubed, okay, minus E of the sum from t equals 1 to t of C hat t a omega t, and from the bound before we had that is less than or equal to 1 over eta log n, and that's not random, so I don't need to worry about expectations on that guy. Okay, plus eta, I think there needs to be divided by 2 on that, sum t equals 1 to t, sum a, the expectation of p of t of a of c hat of t of a of omega of t squared. Okay? So that's exactly the answer from 132, just with expectations taken on it. Okay. All right. So this is the cost of my algorithm. What is the expected value of c hat of a of t? So if I take an expectation on here, I get So I should get the cost of the policy A at that time, yeah? So this is equal to the cost at time t of action A. And if I sum up all the costs, I'm going to just end up with the cost of always following action A. All right? So that is, just to get the number, that is this exercise here, 127. Okay? Okay? And further, which I guess is 129, I think, we had a bound on this as well. If I take the expected value of pt times c hat squared, it's less than or equal to 1 always. Okay? So this term is less than or equal to 1. I think it's 129. Okay? In other words, I've got E of C of x3, so the expected cost of my algorithm compared with the cost of taking some action A is less than 1 over eta log n plus eta over 2. And then since I've replaced this with a 1, I've got t, I've counting 1, t times, and then for each t I'm counting them for each action, and the then action. So it's going to be t times n. Yeah? So notice, that is the cost of my algorithm, that is the cost of some action, and this holds for any action. Okay? So if I looked at this compared to the cost of the best action, I'd do minimization over A. Okay? And that is exactly my regret. My regret is how well do I perform compared to the best performing action. Okay? So that is the regret at time t of this algorithm. Okay? And when I say that, this whole thing here. All of that is the regret of the policy. Okay? Okay, and now we're nearly done. So, and we can have a 10-minute break. So what do I need to do to this to get this bound here? So what did I do last time? So I just look at the parameters of the etas here and minimize over eta. I just choose the eta that's the best one. Okay? So I'll leave you to do that. So minimize right-hand side of 133 over eta. Okay? To mention, there's one thing that's slightly dissatisfying about the result is that if you want to get the optimal bound, you need to know how long you're going to run it for. Yeah? So it's sort of saying, like, I'm going to play this game for 100 rounds, and the parameter I'm going to have to work with is the one that's optimized for a 100-round game. Okay? So basically, eta depends on, you have to decide in advance how long you're going to run the system for. So one of the exercises, the last exercise on the sheet, explains how you don't need to do that. Okay? So you can continuously vary this parameter eta as you learn, and you can still get the kind of optimal learning rates as well. So you don't need to know how many games you're playing for in order for this theory still to work. Okay? So there's an idea that you can apply to kind of extend this. All right? Okay. That will do for now. Yeah, so we'll have a 10-minute break now, and then we'll get onto the sequential investment stuff after the break. Okay.